Okay. All right. Yep. We are recording and we will start now. So the current state of artificial intelligence. So if you have been following deep learning research or just in general, I think you can see that the pace of advancement is very quick and very fast to the point that you we can not really keep up to date because every day, every month, there is something new, like from all the research around the world. And even though when I said in the group chat, no, sorry, in the promotion for the workshop, I said that is the latest trend, the current state. It is actually not that current. It's just that the way, the paradigm that people have been doing at the moment is quite different from the traditional one that you might encounter or even you learn in school. I think, yeah, some of you are like year 3, year 4 from the sign up. I think the one that you learn in school is like neural network, like the fully connected layers and CNN. Those are quite old to some standard. So even though this is latest trend, this is 2021 kind of latest, but it served as a very strong foundation for you to move forward as well. Because if this is a new paradigm that all researcher is leaning towards, there has to be merits to that, and knowing these models and these architecture will be very helpful for your future machine learning application. So what are those? So first is the attention mechanism, which is also embedded in the transformer architecture. So I will not be going through the transformer, but I will focus on this idea of attention because it will help us to understand this vision transformer. There's a paper that is called, an image is 16 by 16 words uh, that you can search. And then we will move on to diffusion model and the idea of multimodality. So diffusion model, because nowadays you can see that there is image generation, which is a rage right now, and multimodality because more and more we're not just classify image or generate text, but we want to inject different modalities such as image, text, voice, etc. Like even in robotics, 3D LiDAR scan, things like that. So having some intuition or like how to even start doing it is important. So let's recap on the component of machine learning and deep learning in general. Deep learning is a subset of machine learning. So the idea should hold. And the idea of learning is that it learns from data. Without data, this method will not work. It is not like an analytical function, like your uh, y equals ax plus b. No, it is not analytical. It has to be trained. So first you have your input. The input goes into the model. This can be a black box. You can sub in, sub out, whatever you want. And then it will produce an output that is fx. So in mathematical notation, fx is just an alteration of the term f, following the function, the alteration of the variable x based on the function f, and we usually also call this a prediction. Then this is a supervised learning paradigm. So there is a label or a ground truth. So here I have annotated with color because that is also a theme throughout the slides that you can notice, is that the input is like bluish, blue or green in the future. The model or the weights of the model is red, is annotated in red. And this green thing here, we call it like a cost or a loss function. So what it does is it defines a function that compare between your prediction and the label. And it will then update the weights with the cost function information, like your gradient. So you know the gradient, you will do gradient descent and update the weights. So the objective is to minimize the loss, to minimize this loss function, and effectively it will make the prediction as close to the label as possible. Yes. So here I want to really distinguish between the blue and the red component, right? The blue and the red components. So I think if you learn about machine learning, deep learning, you will see this node and the connection. People call it neural network, like neurons. So node and connection a lot. It looks like a graph, But what is meaningful, or like how do we use that intuition to help with our implementation? So when I look at the top, the upper one, it is quite, it doesn't give me much information, or it is quite difficult to understand. But then therefore I propose the bottom one, the lower half one, because it is closer to the thing that we are actually manipulating inside the code, or the computer is manipulating, which are matrices, vector, matrices, tensor. Tensor is more dimension, higher than 2D dimension. So yeah, so the red color again signifies the model function with weight parameters, weight or parameters. When you read your papers, the parameters, people usually define them in various terms. Sometimes people use theta, sometimes people use small w, big W. So I just put here for uh, so that you can recognize them when you read the paper, right? But ultimately, they mean they are weights, and they are trainable, as you can do forward and backward propagation, right? They are trainable. So what is the bottom row here? So these signifies the idea of an outer input. So when you put in your input X, right? When you put in your input X, it goes into this function and it gets outer in a way, in some way. And then after that, after the first stage, like the first layer, it will output something like the immediate, this small function will output something, which is this darker vector. And similarly, it will be put into the weight again, some more weight, then output another vector. Then lastly, all the way through the chain forward pass. At the end, it becomes an output. But what is an output? If it is just an outer input, right? The input has been manipulated, has been changed somehow. So why do I keep making a fuss of this? Because that is the frame that I think very helpful when you try to understand the paper, what the paper is telling you, or how is the data flow and change throughout its journey inside the model, right? How it is changed. So it is changed by the data, the input, encounter the weight. The weight will manipulate, right? It is just a mathematical expression. It manipulates, it outputs something intermediate, go in another set of weight, output, go in another set of weight, and at the end, it gives you your prediction, like value output, prediction output that will then be compared to the label. Yeah. So blue and red, keep that in mind when So now I would recap the idea of cosine similarity, and the idea that all kind of data in deep learning is usually represented by vector, by matrices, right? Vector matrices. And why is that useful? One thing that is useful is also the idea of cosine similarity. So if you recall your math, cosine similarity is just a dot product. And if you have two vector, and if you dot product them out, you can have a value. Then this value signifies the similarity between these two vectors, or the general direction that it is pointing towards. So if they are similar, right, the values will be close to one. Okay, when I think when the angle is closer to theta, the cosine will be closer to one. So the dot product of these two vectors are closer to the magnitude of the vector multiplied to each other. So yeah, very close because they are pointing in the same direction. But if the dot product is negative or not equal to one, then it means that these values are in the opposite direction. It is not correlating. Okay, 90-degree is not related at all, and negative is relate in the other direction. Yeah. So how is that uh, meaningful or useful for our understanding? So down here, you can see that the words. So this is a technique used in natural language processing, which is embed or transform the word, our human natural language words, into a set of vectors. And these vectors will have some relationship or a general direction to it. So you can see in the first image, in the top left, bottom left image, You have a man, woman, king, and queen. So man transformed to woman is like a change of gender. King and queen are royalties, but they have a different gender, right? So in this illustration, you can see that the general movement in this data space, right, in this coordinate system vector space is going to the right. So cosine similarity and the way the vector embedded itself in the vector space has that meaning, right? So if this current flow is from male to female, and if this one is changing from the verb with ing and verb in the past tense, and here Spain, Madrid, Italy, Rome is the capital city. So yeah, so this idea of cosine similarity and a general direction in the vector space can embed meaning, right? So where do the meaning come from in these data points? When we just represent them as vector, the meaning comes from their direction and their general like clustering in this vector space, right? I introduced this because it will be very useful. And I also recommended the series by 3 Blue 1 Brown. They just dropped a video that is very, very helpful. And it is the first step to understand your GPT. And because it is animated, you might be able to see what is actually like happening like step by step. I tried to make it step by step as well, but in this slide, it is quite static, but I will try my best. So first is the attention mechanism. If you have been to the transformer workshop we did earlier before recess week, you might have encountered that. But let's recap because this key idea is very important. First, attention mechanism. What motivates us to have this mechanism? The motivating question is that we have a sequence of vector. How do we make these vector relate to one another? So you can see that each of the words can be embedded into a vector, like I mentioned. But we don't just deal with one word, right? In our real world, we deal with a chain of words, right? A bunch of words, and there's a time domain or like an ordering in between that, the data points. So it is not just simply your tabular data that data analysts do, but each of the words can exist in a sequence. And we want these words to relate to one another. For example, if there's I love you, then love is the verb, is a verb being done by I, right? So we would want to embed that meaning, that relationship somehow inside the neural network. So ultimately, what we want is this kind of like attention matrix. So you can see that in the attention matrix, the one that is at the diagonal has higher score, right? 0.8, hello relates to hello. That is quite obvious, right? I love you like basically it relates to itself quite a lot. But then hello and I, love and you, they might or might not have any relationship. Yeah, or have some. And we want to highlight that relationship, that attention between each other. So even though this is a 2D matrix, it only give us the relationship between a 1D sequence, right? It's a one sequence. Hello, I love you. But we want to make each element of this sequence kind of know each other. So an analogy is a covariance matrix. So if you have understand the statistics, so if you have two variables and you do the covariance analysis, each of the variables will be will have some variance with itself, and it will have some covariance with a different set of variables if there is some relationship between them, right? If x equals y, then the covariance is like the same. But if x equals 2y, then now the covariance might be a bit different. So this is the attention mechanism that we want. So we want a matrix that give us a relationship between these words, these elements in the sequence. So there's also a YouTube video that you can follow through. Of course, the way I learned this is also by YouTube video, by reading and searching online. And I find that the visualization is especially useful. So I will be using a lot of block diagram and visualization like this as well. So on the top right, you can see that this is the mathematical equation to get the attention score, but it is quite muddy, right? You cannot feel or see it. You know that is an equation, an expression, but how does it actually work? So let's continue our analogy. We have hello, I love you, 4 words, and each of the words is a vector. Let's say it has a four element vector. Okay. So now in an attention mechanism, we will be these inputs will go through the will go through 3 neural networks, which can be are trainable weights. What are these networks? They are just simply your linear layers, right? Your dense linear layer, fully connected, many names, but they are effectively the same. So QKV stand for query, key, and value. And why do people come up with this structure for an attention mechanism? Because I think they take inspiration from search uh, various research on retrieval or search system. So in a search system, if you have a database, the user will query, like there will be a query, and then the system will match that with a key. And then it will return the value. So if you remember your like dictionary, for example, dictionary comes in a key and value pair, right? So let's imagine that key and value pair is stored in a database, a bunch of key and value pairs. The values might be very convoluted and very big, but the key can be very short and can be compressed quite small. So when a user queries something, the retrieval system has to match the query to the key very quickly. So there's this idea of QKV, query, key, and value. Okay, so now you can see that I need to make a distinction between trainable weights and altered input. So these 4 vectors, after going through the trainable weights, will give the altered input. They are altered in some way. We don't really know. We don't really care on how it is altered at any instance. We just know that it is altered, right? So altered input, and then this term Q and K transpose is trying to make make it into the shape that we just see, which is the length sequence length times sequence length. So it will give us like a square that is very close to the attention score that we want. Very close, but not quite, right? So the dimension of it is sequence length times sequence length. What does it mean? So over here, hello, I love you has 4 sequence. A sequence is 4. The sequence length is 4. So the attention mechanism give us a 4x4 matrix, right? But Q and K are like they are trying to correlate with each other, but there is no value, right? If you there's no value. Therefore, we need to multiply with the V as well to give us the attention score, attention table. So the softmax and square root DK, you can ignore it for now because those are just extra steps. But what I want you to have an intuition is the shape, like how the shape change. This square root DK and softmax are element-wise operation. So even if we use them, the shape will not change. So yeah, so this gives you like the rough shape of how the input is transformed, and they can be multiplied in a way to give a square, and this square is your attention score, and this square will try to relate each element in the sequence. So that is the gist, the key idea of the attention mechanism. So why do I introduce attention mechanism? Because I want to introduce the vision transformer. So, wait. Transformer. Wait, I think I have missed a slide or No, no, no. Okay. Here. Okay. I think I've made a slide. I've missed a slide. Yeah, here. Vision transformer. So, question, why do we need vision transformer? I thought transformer initially is made for natural language processing. That is correct. And usually, and previously, we use convolutional neural network to process our images because the convolution is a signal processing operation. Right? If you're from Triple E, you know, like the convolution, your signal, right? So the idea is similar in CNN as well. So the how is it work is that you have an original image up top here, and then there is a thing called a filter, right? It is smaller than the image, but this filter will convolve through the image like one row by row, line by line, to produce a new input. Sorry, not new, to produce an output. So here you can see that this filter is the trainable weight, where the output is the altered input, right? And we want this because the filter, you can see the filter is also 2D. So in a sense, as it moves through the image, it will preserve the spatial relationship between points. So if this pixel value 6 is next to pixel value 2, then it will preserve that relationship in because if you can see that the filter here, it is follow the same, it's next to each other. So it preserve that relationship. So why attention mechanism? So you recall, if the idea is just to have that relationship, why don't we just abandon the convolutional network and use the attention, right? Because the motivating question of attention mechanism is that we want the sequence to relate to each other, right? We want the element in a sequence to relate to each other. So it will check the relationship between those data points. But the problem now is you can see that in the matrix that we just went through, it is a 1D sequence. Hello, I love you. And from this hello, I love you, you have a 2D attention matrix. So what is the equivalence of a 2D input? So here the 2D, we have 2D inputs. So what is the sequence that we can extract? So we have to break down this 2D image into a 1D sequence. And the way people do that is in this vision transformer paper, they cut an image into squares. Like they cut into squares and then flatten the patches, right? Flatten the patches means, so for example, if this is a 3x3 2D image, for example, then when we flatten it, it will be a 9-element vector of -1, 0, 1, -2, 0, 2, like 1D, right? But instead of flatten the whole big image, we chop them into patches before we flatten them. And if you recall in your natural language processing, each word is a vector. So now each patch of the image is a vector. So that is why it can just we can just use the transformer architecture like directly, because we have processed the input in such a way. So this is why people use vision transformer. It is not because they just randomly throw things together and mix to see what happened. There is a motivation behind it. So the motivation is we still want the relationship between the patches, because they are ordered in a certain way, right? If this is at the top left, it should know that there's a top left. But we also want the attention mechanism to, let's say that, okay, like this is a top left, this is the middle left, and these are like, they are a part of a building, right? So we want that connection, we want that attention, like, because it is a part of a building, then this patch has some relationship to this patch. Yeah, so there is a motivation. And so now, just now, what we went through is a self-attention mechanism. So I think that I can just, abstract this away and say that, okay, the attention mechanism is like that, is the QKV that we have just went through. And now the idea is that we will put in the input. The input is a sequence again. a sequence of vector, and each of these vector is representing one patch of the image, right? So dense, then, and embed are other trainable weights, and then they will alter the input in a Z into a Z intermediate latent space, and then it will go through the multi-head attention. Yeah, so this is the outer input. This is the trainable weight. So what is multi-head attention? So multi-head attention just means that you do the QKV, the attention mechanism, multiple times, right? Multiple times. So there is not one single relationship between the words. Since you do it multiple times, you might have different kind of relationship between the words. So you might ask, okay, like what kind of relationship is there? That is ultimately, we don't know. That is the whole idea of machine learning, is that we want the architecture to try to pick up something, but what it picks up is ultimately dependent on the training data set and the gradient descent. We can only set this up. We don't really control what the weights means. It is only after we train, then we can inspect and see its performance and reason about it. But we ultimately don't know how it will evolve over time. Yeah, so recap, do that QKV to get the attention matrix and do that multiple times for multiple heads, because there might be various kind of relationship between each of these image patches. Right. So after all the transformer, encoder, or attention network, if we have a sequence of 10, so CLS here is just a starting signal. It's a start signal in natural language processing. It will signal to the model that, okay, like we are starting a sentence. So this is just a remnant as we import that over from natural language processing. So we just say that, okay, this is the start of your image processing. And the following sequence is 9 patches of the image. So in total, there are 10, or in this case, N. There are N sequence, N length sequence. And after going through the network, you will get N output vector. But we will only select the first one for our classification. So you might ask, okay, why do we discard the rest, right? I thought we just process them. Then why do we discard them now? It is we discard them because it might make the computation more complex, or it might not be needed at all. Why? Or is it even possible to do that, to just discard? It is possible, because the idea is, I'm also assuming you have your deep learning understanding, which is when the forward pass, it is all up to the dependent on the interplay between the forward pass and the backward pass. So if the forward pass doesn't go to C3 and C3 is not used for anything else, that C3 or that weight will not be involved in the back propagation, right? So back propagation will trace back the calculation that get it into that point. But if we don't use it, then there's no involvement in the future steps. So the weight will update accordingly, as if the model is only using C0, right? So to recap, this transformer encoder network has the capacity to process and output N vector. But based on our architecture, we only select C0 for the subsequent processes. And because of that selection, the rest is discarded and it will not be affecting our model. The weight will update as if this vector is not being utilized. So it will update accordingly. What does that mean? So it means if we want to use this structure to classify our image, right, then the weights will update accordingly using only C1 to get our classification correctly. So yeah, softmax classifier in P. This purple vector is your different classes. Each element is each class, and it will output a probability of the class, and we can classify our image. Yes. So far, do you have any question so far? on the attention and the vision transformer. So this is the first part of our talk of our workshop today. Revise the attention and the vision transformer. So this is important, or this is the latest trend, because the attention mechanism is very powerful. Because ultimately, what do we want to do with deep learning or machine learning? Is we want to find a relationship between our input and our output, right? If we see a cat, the cat has a certain shape, has a eye, ears, color, something like that. We want those pixel or like those features to mix, to match or to make sense, right? There is a meaning in those blob of fur, and we want to understand what is the connection or the meaning behind that. So by having this attention mechanism, we are telling the pixel that, okay, like this pixel is related to this pixel and there is some meaning to that. Yes, so therefore transformer or attention mechanism is used in many domains nowadays. Text, vision, audio, a lot of things. So I hope this introduction allows you to understand how it is the attention mechanism started in natural language processing, but now it is creeping to other domains. And vision transformer is one example of how it is doing that. It is creeping to all over domain. Okay, then let's move on. So multimodality. Yeah, right. So you have heard of multimodality recently by various companies saying that, oh, our model can understand images, can understand text and audio, and it will generate the output that you want. So it is seamless. You don't have to have different specialized model, for example. So how do we get the multimodality in our machine learning architecture? So we go back to our idea of data types. Ultimately, all of the data type, all of the modality, all of the sensor reading that we can capture from the world will be represented as vector, matrices, or tensor. And how do we make use of these data in the model? So here are some example. Tabulated data are vectors. Images are 2D patches, 2D images with different channels, RGB. Videos is just a stack of images. Text embedding, like I said, one text, one words, we can convert that into a vector. So how do we deal with that? So there is this idea of fusion. It's very simple and naive way, which is you can flatten that, right? Similar to the 16 by 16 patch that we shared just now, that we see. At the end of the day, you can just, flatten it to make the computation easier. But sometimes flatten it might not always work, and it is very dependent on where you flatten that. So different image channel, so you just flatten them out into like one piece. So if you can see here, like 7 by 7 times 512. So it means that this is an image. So this is an altered image. So you see what is being done here. That image is being altered. The input is being altered into this stage where it is 7 by 7 by 512, right? So this is an altered input. And then we will flatten it out into like one vector, one thin vector of 114096. Yeah, so that is how we ultimately convert 2D to 1D. And then there's this idea of concatenation. It's just, piece them together. Done. That is how we fuse. That is how we get multimodality. Right. So down here are the various way that we can do that. For example, image. If we have image and like tabular data, which are like two separate things, how do we even make sense of them? Right. So we can have like some CNN model, some processing to get into some dimension, squeeze it into a smaller dimension first before we add them in together to form a bigger altered input. We call that altered input. And this altered input will be passed through the next one, like the next processing step along our architecture. Or we can do tabulated data and then we process that, bloated it up, blow it up somehow to get a 2D version of it, and then we slot it into our image as another channel, right? 4x4. Depends on how you envision it to be, or how, again, you will have to test it and see the previous research to get the recommended or best practices. Because ultimately, if we want to be a 2D, it has to have some spatial meaning, right? If we are using CNN or CNN again, then it will scan through and there is some spatial meaning to the 2D elements, 2D data. So tabulated scalar data, and then you transform it into 2D, probably might not be a good idea. Yeah, but it is a possibility. So big picture summary is just concatenate them, just add them up or multiply or add in somehow. But you have to be careful on how you do it. Yeah, so these are various other different ways. And this fusion occurs in different steps as well. It can occur in different steps. Ultimately, you decide, the architecture, the architect of the architecture, decide where do you want to add these modality together. So you can do it late fusion, yeah. So after you classify, after you process it, then you combine at the end. Or you can do early fusion, like, oh, I get the raw data, I add them in together before I go through the pipeline. Or joint fusion, which is text and mapping, whatever, pooling, then classify. That pre-process one first before you add the other one. Yeah, and then down here, it is a time domain thing. So what this paper is trying to do is to classify a video, and at the bottom, you have like different images of that video. And the way they classify it can be, okay, like I just use a single frame, right? Or I can use the start and the end frame. Or I can use like a window of frames, then add them together and then go through the same pipeline, right? So there are few ways of fusion or selecting what to add, what to concatenate before push it into a model. Yes. So those are the multimodality, the naive way. There are definitely more advanced way, and we will be exploring them right now. But before we explore that advanced way or the current way that people do multimodality, let's introduce you to diffusion model. So you might have seen like image generation nowadays, and how do people generate image? There are various methods, but one of the popular one right now is diffusion model. So why is it called diffusion? Because it is a reverse process of diffusion. If you study physics, right, thermodynamics, or you play with liquid chemistry even, you know that if you put a droplet of food coloring into your cup of water, the food coloring will diffuse, right? Diffuse from a position of higher concentration to low concentration, and it's spread out. Yeah, basically spread out. So the idea here is you have an image, which is a very well-defined image, have sharp edges, has a color patch over here, over there. But let's say we want to mix and match that. We want to make it a noise. It is not a clear signal anymore. We want to make it into a noise. Then we add Gaussian distribution, like add random noise to it. So on the right, you can see that it is like fully noisy, fully like static, your TV static. And the task is to generate the image from a static noise, right? In order to generate this noise, it is quite easy, right? We can just tell the machine, okay, I want randomly sampled Gaussian noise that is shaped in a 2D shape. Give me. It can do that. The computer can do that. But because it is ultimately just a sampling equation, right? A random number. You call Python, you call numpy dot random dot ran int or ran. But to tell the machine, okay, I want an image of a sunset, The machine doesn't know what a sunset is. The machine only knows the noise. And the task is to convert that noise into an image. So that's why diffusion, right? Diffusion is the forward process. So how do people do that? So in the training pipeline, they will generate that noise from a clear image. So you can see that over time, it will add the noise over time. And at the end, it is a Gaussian distribution, mean at 0 and 1, right? Mean at 0, variance 1. And what we want to do is to reverse that process using our model, our machine learning, deep learning model. Yeah, so you see that the noise go in, and when it come out, it is less noisy. The rationale being that going from noisy to the clear image is very hard. So we have to do it step by step, so that it is more feasible to do so. Right? So how do we achieve that? So the forward process is easily computable. It is just telling the computer to add, we have a clear image, and we just add noise to it, right? It is a simple process. Converting the noise back to an image is hard, and it requires machine learning. It requires a lot of data points. But the forward process is easy. So the forward process is used to create the label, to create the ground truth for our supervised learning. So you can see that each of these images is a label, and the diffusion model, it is the same architecture, it's the same weight. It's just that if we put in different input, it will get us a different output. So you can see here, if our noisy image is at this stage, we put in the input, the model will produce some output, and then you see this green dumbbell. So the green dumbbell is saying that, okay, you have given me some output, sure, but is it close to the ground truth? Therefore, it has to compare between the ground truth and the next step. So now, since we are going reverse, right? We are reversing the direction. We are going to the left. Then this is an input. So we want this to be the ground truth next, ground truth output. Yeah. So we put it in diffusion model, and when we compare, and after we compare, we have the loss function, and using the loss function, we can tweak the weights of the diffusion model. I hope this is clear. So again, recap, the forward process, simply add noise, which is an easy task that can be done by the computer. And at each time step that we add noise, it will be our ground truth. The resulting image with the noise is our label for that time step. And then we use our deep learning model, input time step T, let's say T, put it in, then compare the output with the ground truth label of time step T minus 1. Yeah. To update our weights. And continuously, like we put it in. So we recursively put in the diffusion model. So for example, if we say that, okay, we have, this is 7, we have 7 steps to go from clear image to a noisy image. Then in order to reconstruct a clear image from noise, we have to go through 7 steps, right? The diffusion model, go through once, go through twice, go through 7 times, and at the end, hopefully we will get a clear image. So what is the architecture of the diffusion model? I think at this point, if you don't have background knowledge of the U-Net, it is all right. You just understand it as CNN based. And if you understand the U-Net, then I think it can be self-explanatory. So what is it doing is similar to the CNN. There is a filter, right? The filter goes through line by line of the image, and it will produce a smaller altered input. We call that altered input. And as it change the input to become smaller and smaller and smaller, at some point, it will then upscale, like sampling that input, like back up. Why do we do this? Why do we go down and go up because we want to preserve the size of the image, right? If you recall, we want to, let's say if this is 100 by 100 pixel image input, we would want it to be 100 by 100 at the end as well. So some people might ask, oh wait, so if that's the case, why not have a very large convolutional network that keep the same size at each time? Why does it have to shrink down? Which is a because as you shrink down your image, your outer input image, the kernel will encompass bigger region of that image. I don't know if I'm making sense because I think it is out of scope of this workshop. So I think I will just leave it here, right? UNet, CNN based. Yes, let's move on. You just know that if you understand how it is updated, right? How the neural network is updated, that is good enough because it is the same idea as well. You set up the model in a certain way and the update step will handle the updating for you. You don't have to care if there is any part that is left out. If there are parts that is left out, it will not be considered in the update step. So in a sense, as AI engineer, you just set up the architecture. You hope you make sure that the architecture makes sense. Then you just keep pumping data and it will train the weights. And hopefully it is accurate. Yes. So, okay, it's closer to the end already. So what is the output of the diffusion model? So we go from the noise to an image, right? Yes, but if every clear image, like an image of a dog will be transformed into a noise, an image of a beach, of the beach will be transformed to noise. So now if we want to go back from noise, we want a beach, but we don't have any more inputs to the model, then it will just randomly generate some image that we don't want. So we don't have any input. So from this noise, it can generate a dog, or it can generate a cat, or it can generate whatever it can. It can whatever is in the data set that it knows. Right, random image generated. So how do we make it generate the thing that we want? So we have to add text, right? We have to inject the understanding of text into this model, right? So it has to be guided by text prompt. So that is the whole idea of your Stable Diffusion, your Midjourney, your DALL-E by OpenAI, your image generation AI. So that leads us to this model by OpenAI called CLIP, Contrastive Language Image Pre-trained. That is a mouthful. But the idea is that instead of doing the fusion, like I mentioned on the multimodality, they do it a little bit differently. They go back to use the idea of a cosine similarity, right? And they also have the text encoder and image encoder quite separate as well. So here is the big picture. So there are two parts, and I will be going to the two part right now. But the idea is the image classification is transformed into a text similarity problem. So it is not you have an image and then you push it through an architecture, and then the architecture will give you a label of dog or cat or image. But it will give you the output that is in terms of a sentence that is the closest in describing the image. Let's see how it works. So first, okay, I need to maybe do this a bit, delete a bit so that it is not quite overwhelming. Right. So that is not very overwhelming. Okay, let's go. Right. So they scrape the internet. First of all, to get the training data point, they scrape the internet for image and the caption. So there is as labels. There is not really labels, but there is a pair of image and text. So for example, here is Aussie the pup, Aussie pup, and the hamster on the grass, and many much more in the data set. Then there will be a text encoder and an image encoder in there. So the text encoder and image encoder are trainable weights. Again, the idea, this is the one that is updated by the gradient descent. So Pepper, the Aussie pup, goes into the text encoder, converted into a T1, which is a vector that parameterized Aussie, the puppy, the Pepper, the Aussie pup. Hamster on grass is converted to T2. Yeah, some vector, some sequence of vector. Then the image is the same. The image goes to image encoder and give you back a string of vector, not a string, give you back a vector. That is called an embedding. So I1, I2. So the embeddings are, again, altered input. Those are not weights. Those are altered input. And different inputs will have a different altered input. Then we do cosine similarity, right? We do the cosine similarity on these pairs. So T1 and I1 should match each other. T2 and I2 should match each other, right? So we have this square of cosine similarity. It is not the same as attention. This is not the same as attention, but it makes use of the idea of cosine similarity because we were trying to match this T1 and I1 together. Then, yeah, you might ask, okay, so where is the label now? So the label is not image, or it is not Aussie, the Pepper pup, Pepper the Aussie pup, sorry, Pepper the Aussie pup. It is not, those are not the labels. The label will be on identity matrix because, so that is what we want, isn't it? I1 and T1, because they are the same. They match with each other. This T1 embedding and I1 embedding should point to the same direction in the vector space. So that is what we want. So we want I1 and T1 to equals to 1. And the rest is all 0, right? So in a sense, this matrix, we want to compare and contrast against our identity. And therefore, there is a loss function. I should have used this one because I have been using that, right? Yeah, I should have used this. So loss function, you compare and contrast in order to back propagate and train our weights, train the text encoder and the image encoder. Yeah. So after it is trained, after the text encoder and the image encoder is trained, we will be using them for our prediction. So let's say we have a class, different classes of plane, car, dog, birds, a lot of labels. But we don't just put the labels in as one word. We put them as a sentence, like in our training data set. So we put it as a photo of a plane instead of just plane. Then this whole sentence is then encoded as T3, an altered input. Recall, altered input. The photo of an object is altered into a text vector. Similarly, the image encoder is also converted into a text, an image vector. I'm sorry, an image vector as well. And then we do cosine similarity. And then we do softmax, see what is the highest score among these. And it will pick, let's say, if it picks a photo of a dog, then it is a dog. Then we can just chop off the dog part of the whole sentence and say that it is a dog, right? So cool, right? Like it is the paradigm is quite different, right? It is not one single big block that you put in the image and it will output a text. No, this is based on the training of the encoder in a way that give us this similarity matrix. And from this similarity matrix, it will get us the prediction based on this embedding, image embedding, and the text embedding. So it is trying to match the description of the text and an image. So probably if this image is called a black dog in the forest, for example, a black dog in a forest. So black dog in a forest is not exactly our list of sentences. The list of sentences contain only a photo of blank. There is no dog in a forest. There's none of that. But because we hope that the text encoder and the image encoder has learned enough from the training data, the vector, right? The vector that points a photo of an object of a dog, let's say a photo of a dog, should be quite close to the text, let's say a dog in a forest, for example. And because of that closeness in the vector space, hopefully the cosine similarity will come out as the largest among these possibilities. And if it is the largest, then we can use softmax for classification. Yes, so that is one very interesting way that they combine text embedding and image embedding. Right? There is no fusion, no concatenation of anything. So that is one way to do modality, multimodality as well. So how do you get to know this? I think it is to keep up with the current research paper, because different people who have brilliant ideas keep popping up every day. This is one of them. Yes. So one way to do multimodality. Then how do we inject that to our diffusion model, right? So now we would have that same text encoder as a part of our diffusion model. So this is the two step, right? The two step of our reverse process in the diffusion. So from a very noisy image, we put that as an input, and then there's also a prompt that is called sunset. And when we put through the text encoder, it will be something more meaningful. It will have embedded the idea of the text. And then, yeah, it will go through the UNet as well, or some way, somewhere, and will be fused, right? Fused into the model. And the output, hopefully, will have some sunset component to it. And then for the next step, this quite blurry, quite noisy image is act as an input. The prompt is still the same. Go in, the output will, yeah, will become clearer and clearer and resembling the sunset. Yeah, so that is the big picture, the whole idea basically. So that is how people can inject the prompt into the diffusion step. And here are the two collab links on the Vision Transformer and the clip for those of you who are interested. But I think I will not be going through, because like I said, I want to keep this concise and maximum visualization and understanding for you. And I know that it is already week 11. So I also don't want to keep you any longer, right? And all of these are quite high level and very up to date by the standard of 2021. So I also don't, and I also think that it will take quite a long time to digest. So giving you a lot of things to understand at the moment is quite tough. So I think I will stop here. Do you have any questions? Hi guys, do you have any question? If not, I think that is all for me. And I will also be sharing the recordings and the slides. Hello. Okay. Yes. I see a thumbs up. I see someone unmute themselves. Do you have any question? Junction. Okay. Then if not, I think we can end here. Uh, Okay, thank you very. Oh wait, actually, yeah. Can you at least, let's say, type into the chat, because I didn't have the feedback, but maybe you can type into the chat. How is the content like? Because this is the last workshop for MLDA. We have planned a workshop series, and this is the last. So we are trying to do something that is new and up to date. But I understand that it can be quite difficult and challenging. So if you have any comments, you can type here. A quick one would do.